So this video is going to look at covalent bonds, but drawing what we call more complex dot structures. So there's going to be a set of rules that we're going to kind of follow when we're doing these. But for this exercise, again, you're going to need a periodic table to refer to for your valence electrons. So what I would do is probably pause this video so you could see what I have in terms of taking notes, or just follow along as I describe it, but I'm not going to go super slow on this. So for these more complicated structures, what you're going to do is kind of a step-by-step of how to approach these drawings. First thing, you're going to count all of the valence electrons that you have in the molecule. So you're going to add up all of the electrons from every atom that is attached in this molecule. You're going to put the first atom that is listed as the central atom. There is a way to actually determine what the central atom is. We just do not cover it in this course. You're going to join that central atom to each other atom. So essentially, you're going to make a single bond at first. Then you're going to satisfy the octet around each atom. So if that means you have to add a lone pair or whatever has to be done, you're going to then complete the octet. Then at the end, you're going to count the bonds and the lone pairs around that and see if you have the same number of electrons as you started with. So it's a way to kind of double check that you've done everything correctly. So when we are drawing these molecules, there's going to be these steps are going to be what you follow. And then there's some little schematic things that you're going to have to pay attention to. So we are going to draw what we call some polyatomic ions. So these are ions that we introduced to you guys very early on. You just use them as a plus or minus. Most of the time they were minuses, and you were putting them together in ionic compounds. But now you're going to actually learn why they are what they are based on the fact that they make what we call covalent bonds. So this is PO43 minus. This is called phosphate. And there is a particular way that you're going to draw it. So the first thing I'm going to do is count up all of the valence electrons. So I'm going to start with phosphorus. Phosphorus in the P3 column, so it has 3 electrons in the P orbital and 2 in the S. So phosphorus has a total of 5 valence electrons, plus oxygen. So we have oxygen here. Oxygen is going to have a total of 6 valence electrons, but I have a total of 4. So I have 6 valence electrons times 4, okay? And then I have something that is different, something we haven't talked about yet. So if I look at this -3, that means 3 electrons have been donated to this molecule. So I'm going to add 3 valence electrons to this overall. And you will find that these valence electrons are coming from a metal or from the other part of the ionic compound. That's where they're coming from. So this ends up being 32 electrons. So that's how many valence electrons I have in this total molecule. So that's the first step, count the total valence electrons. Now, I'm going to draw lines in my structure. So I'm going to divide this number by 2. And you're going to see that in my notes a lot. So when I draw them with lines, every line is 2 electrons. I'm going to count lines. So I want a total of 16 lines in my final structure. So this is the big jump for you guys, okay? So when I look at phosphorus, I draw it with its 5 dots around it. And when I look at it this way, you're like, wait a minute, it could only make 3 bonds, but I have 4 oxygens attached. So what I want you to think about with these valence electrons is these electrons do not belong to phosphorus anymore. They belong to the whole molecule. So the analogy I make is like if you're going to a party and you're supposed to bring something to the party. So you're in charge of cupcakes or the soda or the snacks, some kind of snack. You are going to share it with everybody at the party. So these 5 valence electrons do not belong to phosphorus. They belong to phosphorus and the 4 oxygens. But spreads out these valence electrons to complete everybody's octet. So just like going to a party, you're trying to make everybody happy. So you're going to share all of your cupcakes. So I'm going to put phosphorus in the middle. So I'm going to put the first atom listed as my central atom. Then I'm going to join the central atom to each other atom. So I have 4 oxygens, so I'm just going to draw a single bond of oxygen out that way. Then the next step is to what we call satisfy the octet around each atom. So oxygen needs some lone pairs in order for it to complete its octet. So I just draw them in here. And then I check my phosphorus to make sure it has 4 lines around it, which it does. So that means it's completed its octet. So I now count all of my lines. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So if I have 16 lines, which is what I need in this structure, this is a legitimate structure for PO4 3-. Now, there is a little bit of schematics or format that you need to be aware of. When it has a charge on the outside, you need to put brackets around the whole structure. So draw the brackets around the whole structure. And then you're going to put a 3- on the outside. So whatever that charge is going to be what you write out here. What you're telling the reader is essentially, I have 3 electrons that have been donated to this structure. If I did not have those 3 electrons, I cannot draw the structure. I will not have the correct number of lines. So you're going to put brackets around anything that has a charge and put the charge on the outside. So see if you could do SO4 2- on your own. So SO4 2-. So count up the valence electrons, put sulfur in the middle, attach the oxygens, and see if you can complete the octet. So please pause the video, and then when you see it next, you will see an answer. So as you could see, it had 16 lines to be drawn, 32 valence electrons, so very similar to the one we just did. Sulfur in the middle, then 4 bonds around it, attaching the 4 oxygens. Again, don't think about it. I got 4 oxygens, I attach them, I complete their octets, and then I put the brackets on the outside and put a -2 to tell the reader that 2 electrons have been donated to this structure. Okay, so let's take a look at another example and kind of show you something else that could possibly happen. So this is SO3 2-, SO3 2-. So this is sulfite. This is sulfite. SO4 is sulfate. Again, we did not emphasize naming that much, but this is sulfite. So sulfur has 6 valence electrons. Then I have 6 valence electrons for the oxygens, 3 times that. And then I have 2 electrons that have been donated from someplace. So now I have 6, and then plus 18 plus 2 gives me 26 valence electrons. I divide that by 2 to get 13 lines. All right, so just like before, I put sulfur in the middle, but now I only have 3 oxygens. I only have 3 oxygens. So I'm going to go 1, 2, 3. And then I'm going to complete the octets around oxygen. So I'm going to go like this and complete the octet by adding lone pairs. So if I stop right here, I have a total of 4, 8, 12 lines, and I need a total of 13 lines. But what I should see is sulfur only has 3 lines around it. Okay, and sulfur is not a weird exception that we need to worry about. So these 3 lines, I have not completed the octet on sulfur. So you can put a lone pair on that central atom. And where you draw it, it doesn't really matter. So when you see this, don't freak out or anything like that. So that is where you put the lone pair, and then you put brackets around it, and then you put the -2 on the outside, -2 on the outside. So I would like you to try to draw CO3 2-, CO3 2-. And this is called carbonate. So CO3 2-. So see if you could draw it, and then I'm going to pause the video, and then I'm going to have some things written out for you. So try it first. So CO3 2- has a total of 24 valence electrons. So I should only have 12 lines in my structure. So if you put carbon in the middle and you put 3 lines around it, and then you complete the octet around oxygens, you're fine with 12 lines. But carbon needs a lone pair on it because it does not complete its octet. And carbon will always have 4 lines around it, always. So this is 13 lines. So this cannot be the structure. Okay, so what you're going to find with some of these, you might want to use a pencil sometimes so that you can see if you make a mistake, you can kind of erase things and try again. So in this original structure, everything was single bonded. Everything was single bonded. So what if we did a double bond? Well, if we draw a double bond on one of the oxygens, which is perfectly fine, I could only put 2 lone pairs on that oxygen. So that's going to then essentially satisfy the oxygen's octet with that double bond and then 2 lone pairs. So I can draw it with this with 1 double bond in it, and again, including the brackets and the 2 minus. But could I draw that double bond with that oxygen? You know, are there any rules of which oxygen I could draw it to? Can I draw it to that oxygen? Okay, including the lone pairs. Again, I will draw in the lone pairs so you don't get confused. So that double bond could actually be in all 3 locations. Okay, so it's something called resonance. Okay, so resonance is occurs when you can have multiple electron dot structures. In reality, the electron is actually in all 3 locations. We're not going to go there in this class, but that's what we kind of talk about later on if you take chemistry again. So resonance means there's multiple electron dot structures that can't be drawn. So instead of you drawing everything out, what you're going to do instead is put the double bond in one of the locations. Okay, make sure you draw it correctly with brackets around it and a 2 minus. But what you're going to add to this drawing is a double-headed arrow underneath it. That means in chemistry that this structure has resonance. That double bond could be here, it could be here, it could be here. So you don't need to draw all 3 of them. You just need to draw a double-headed arrow. Now, please realize you should not do a double-headed arrow around everything. Okay, you just things that have resonance, just things that have resonance. All right. So see if you could draw SO3. See if you could draw SO3. So SO3 has resonance. SO3 has resonance. So that double bond has to be in one of those locations in a double-headed arrow. But I have done something wrong with my drawing here. I do not need to include the brackets. Okay, the brackets are not necessary. So I really should have drawn it as S double bond O, oxygen, oxygen, lone pairs, and a double-headed arrow. So if I have no charge, so there are some covalently bonded molecules, these are both non-metals, that don't need brackets because I don't have any electrons that are being donated to me. So I just draw the structure and the double-headed arrow underneath it. So I wanted to show you one that didn't have the brackets so that you can see that sometimes you don't need the brackets. It's only when you have a charge, only when you have a charge. So to finish this up, there are some exceptions to the octet rule. Okay, so hydrogen, lithium, beryllium, and boron will never satisfy the octet rule. Now, there's some other things that are out there, but those are things that we're not going to cover in this class. So this only makes 1 bond, 2 bonds, 3 bonds. So if you want to write bonds, hydrogen only makes 1 bond, lithium only makes 1 bond when it makes a covalent bond, beryllium makes 2 bonds, boron makes 3 bonds. So they will never satisfy the octet. Everything else I'm going to give you, you need to see 8 electrons, 4 lines around the structure. Otherwise, it's not a legitimate structure. So again, that's the way to draw some of these complex molecules. So you have to kind of go step by step